Hello everyone, I'm Berke. In this video, we will be talking about a recent experiment on cloning of quantum entanglement. It is first important to note that the term cloning might be misinterpreted. It is actually impossible to clone a quantum state, but imperfect cloning might be achieved through various methods. Approximate quantum cloning of single particle states has been tested previously and it is achieved. However, experimental cloning of quantum entanglement, a highly non-classical correlation, remained unexplored until this point. Let's see the table of contents of this video, that is the outline. We will first talk about quantum terminology. We will see some terms that we will encounter in the future. And then we will go to quantum information and talk about why it is impossible to clone. Then we will talk about quantum entanglement and what makes this experiment special. And at last, we will talk about the experiment itself by first talking about the concept and then the setup. Quantum state is a mathematical entity that provides a probability distribution for the outcomes of each possible measurement on a system. For example, let's talk about a familiar case, an electron in an atom. This atom, if not observed, might be in superposition. And in this superposition, the quantum state of the electron might be spinning upwards or downwards, or with more familiar terms, +1/2 or -1/2. As the electron is in both states, we can express the state of the electron using this equation. You see, we have a constant 1/√2. This constant is useful in the wave function of the electron, and it is entirely a different topic. Moving on, we see the upwards arrow and downwards arrow. This means spinning upwards, and then minus the opposite possibility, that is spinning downwards. The weird symbol these arrows are in is called bracket notation. Bracket notation is used to describe a quantum state, and that is all. Then we have state fidelity. State fidelity basically means the resemblance between two states, and we will use this when we compare the clones with the original ones. And then we have polarization. Polarization is an interesting topic. When the light travels, it travels in multiple directions using multiple planes. But when it goes to the polarizing filter, it comes out traveling in only one direction. That can be horizontal, vertical, diagonal, but it can be determined with the polarizing filter. Now let's talk about information and exactly what we are cloning. So we are familiar with classical information actually. Using computer terms, a classical information can be described using bit, and combination of these bits can create bytes to represent an information. For example, let's see this combination of bits. You see this byte means the letter A, and consequently, same thing can be applied with quantum information. Let's see an example. So we have an electron that can spin upwards or downwards, and a combination of these states, for example, downwards, upwards, can represent an information. In this case, if we say when it spins downwards, it's 0, and when it spins upwards, it's 1, then this aforementioned combination can be used to convey 0, 1, 0, or in base 10, 5. Now let's consider a case when one of these electrons is in a superposition. That means it's both spinning downwards and upwards at the same time. So in the last example, the last electron is in a superposition, and because of that, the quantum information can be either a 4 or a 5, and since it's in a superposition, it's both of these. This particular property of quantum particles is used in quantum computers to convey information much rapidly and efficiently. Just like how bits are used to convey classical information, qubits are used to convey quantum information. Because of the uncertainties, the things you can do with quantum information is much different than classical information. The limitations to quantum information can be described using 5 theorems. The first of these theorems is no teleportation theorem. This theorem states that a qubit cannot be wholly converted into a classical bits, that is, it cannot be read. The non-cloning theorem states that an arbitrary qubit cannot be copied. The non-deleting theorem says An arbitrary qubit cannot be deleted. The no-broadcast theorem states that although a single qubit can be transported from place to place, for example via quantum teleportation, it cannot be delivered to multiple recipients. And the no-hiding theorem states that quantum information within the universe is conserved. This experiment is particularly interested in the second theorem, yet it is important to see how all theorems are interconnected. Before delving further to no-cloning theorem, let's talk about quantum entanglement. Quantum entanglement is a phenomenon in which unknown states of two or more particles are interconnected. To elaborate on this, let's consider the electrons in an atom case again. By Pauli exclusion principle, we know that two electrons in an orbital cannot occupy the same state. Thus, if one electron is spinning upwards, the other must spin downwards. However, if they are not observed and in superposition, both of these electrons are spinning upwards and downwards simultaneously. As soon as you check the state of one, the superposition and the entanglement collapses. For example, you check one of these electrons and found out it's spinning upwards. What do you think happened to the other electron you did not check? Is it still in a superposition? It cannot be, because now that you know one electron is spinning upwards, the other electron must spin downwards, and only downwards. Instead of electrons, this experiment uses photons. Remembering the polarization idea, let's say we have two filters now. One of them converts a light to travel through a vertical plane and the other through a horizontal plane. Let's see we send two photons and then when the photons comes out, we don't know which one is traveling vertical and which one is traveling horizontally. Again, we see a quantum entangled state. The joint state of these quantum entangled particles can be expressed using this formula. We see horizontal state times vertical state minus vertical state times horizontal state all over root 2. What this equation means that if one photon is traveling horizontally, the other must travel vertically. This is one possibility. And then the other possibility is the first one is traveling vertically and the other one is traveling horizontally. Thus, this forms a quantum state and it is expressed using this formula. Now that we got a sense of what quantum entanglement means, let's talk about the no-cloning theorem again. So we will prove why it is impossible to clone a quantum state. So here we have a quantum state to be cloned, and next to it we have a dummy state. So these two go through a unitary transformation. A unitary transformation is a transformation that preserves the inner product to produce multiples of these products. Let's say our quantum state is a state of a photon that is in a superposition of traveling horizontally and vertically, created by using the polarization idea we talked about. So we want to clone this superposition. So we want to clone horizontal state plus vertical state. After the cloning, we got two of these states, which means we got a horizontal state plus a vertical state, and then as we have one more of these, times horizontal state plus vertical state again. Now, let's look at the idea of cloning in a different perspective. So what we are actually cloning is the superposition of the photon, right? So instead of cloning the whole state, we can clone the horizontal state of the photon and then the vertical state of the photon separately. We are going to use a distribution property of transformations, which is identical to that of mathematics. For example, if we have A times, in parentheses, B plus C, we know that this is equal to AB plus BC. The same idea can be used in transformation as well. When we do that, we first have two horizontal states, which are multiplied together, plus two vertical states, which are multiplied together again, because at the end we have two quantum states. That's the idea of cloning, right? As can be seen, by approaching to the idea of cloning in two different perspectives, we have found two different results. This just goes to show that the cloning theorem is disproven using mathematics. This proves that either perfectly cloning is impossible or quantum physics is wrong. And since quantum physics is experimentally supported to be accurate, we believe that cloning is impossible. It's time to look at the experiment and how they managed to imperfectly clone quantum entanglement. To speak broadly, what we want to do is first create an entangled pair of particles and then clone these particles using dummy particles so that the dummy particles can become the clones of the entangled pair, thus creating a cloned entangled pair. To achieve this, the experiment used a 1 to 2 single qubit quantum cloning machines, abbreviated to UQCMs. This machine works by taking a quantum state and two dummy particles as inputs, and through unitary transformation, which I explained earlier, it creates two clones of the quantum state. As we only want one clone, we discard one of these clones. Now that we got a sense of how to imperfectly clone a quantum state, let's see how we can clone a quantum entangled pair. The idea is pretty similar. First, we create the entangled pair, and then we separate these pairs into two different UQCMs. Inside these UQCMs, two different pairs of entangled states are already prepared. So when the quantum state we want to be cloned enters the UQCM, it meets with these two different particles, and then at the end it produces two different clones of each of the particles. After we discard each of the extra clones, we are left with first the quantum entangled state we originally prepared, and then the newly formed quantum entangled pair that was created using two different UQCMs. Conceptually, the experiment is as basic as this. Now let's talk about how this experiment can be performed in real life. The experiment uses beta-barium borate crystals, abbreviated as BBO, to create two independent photon pairs, currently not entangled. Then they are combined into one path by bifringent beam displacers, abbreviated as BDs, and half-wave plates, abbreviated as HWPs. After each photon is reflected by tilted BDs in a special angle, the photons go through polarizing filters, where at the end they become entangled, which means they are in a superposition of vertical or horizontal traveling, as we discussed earlier. The same procedure is applied to the dummy particles, which are known as Akida qubits, to create entangled pairs to be used in the cloning process using a UQCM for each. Through such entanglement, we have three pairs of quantum entangled photons, each with the quantum state equation shown here. As we explained earlier, the photons are in a superposition of horizontal and vertical traveling. So if the first photon is traveling horizontally, the second has to go vertically. And if the first one is going vertically, the second has to go horizontally. And thus the reasoning behind this quantum state equation. These are then traveled with optical fibers, known as SMFs, and guided for the partial bell state projection operations, and they meet simultaneously. The experiment uses two non-polarizing beam splitters, known as NBSs, to carry out unitary transformations, which finally creates the clones. At the end, the extras are discarded and the particles of interest are detected. Polarization measurements are performed on these photons for their states to be determined and to compare the photons to deduce state fidelity. Let's see the results of the experiment and why it is particularly successful. So here we have our graph. Our x-axis is the states of the photons. So we have horizontal, 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 vertical, vertical, horizontal, and vertical, vertical, as we talked about. And we also have, the experiment also used different polarizing filters. So other than horizontal and vertical ones, they also had diagonal ones and also spherical ones.
The vertical axis
And in
shows
each
them
of
at
these, we
times
see
the
the
photons are
match
getting
between
reflected.
local transcript and the distant ones. So local transcript is our original input after the transformations. So it is slightly changed. And distant ones are our cloned ones. We can also check the resemblance with the topographic graphs. So part C and D are basically what we have here, local transcript and distant. We also have our original inputs, and we see there is a difference between these. So our original input was either horizontal or vertical ones. So it's not a perfect match, but the experiment claims that it has still over a 50% state fidelity. Therefore, this experiment was found to be the first experiment to clone quantum entanglement, which opens a window to a great future. To summarize, we created two photons and then entangled them via polarizing filter. And after they got into a superposition of horizontal and vertical traveling, we then used two unclear qubits that were gone through the same procedure. And then we cloned using non-polarizing beam splitters as universal quantum cloning machines.
At the end, we had a state fidelity of greater than 50%.